Hello everyone, I'm Zeyu Wang from Zhongxin University. Now, I'm going to introduce the paper named Plot2API, recommending graphic API from Plot via semantic parsing guided neural network. My presentation will include these 5 parts. Firstly, I would like to introduce the background of our research. As we all know, figures and plots are the indispensable tools for data visualization. In software engineering, almost all the programming languages support such functions and possess a series of relevant APIs as one of core libraries or packages. It is very common for the software developer, particularly the beginner, to search API on the web, based on a case figure for guiding the plot. The right figure shows a help post where a developer asks how to draw a figure like the one posted in Stack Overflow. What's more, people might want to know the APIs starting from a plot, such as imitating visualization styles. In agile development, developers often sufficiently utilize the materials of previous projects for speeding up the development. Thereby, they expect to convert the figures plotted in one language into APIs of the other directly to reduce the time cost. In these scenarios, a tool that can automatically recommend the graphic APIs based on a plot can provide guidance for developers and improve their productivity. Therefore, we present a meaningful task in software engineering and data visualization, which is plot-based graphic API recommendation. Our goal in this paper is recommending graphic API from plot. API recommendation is not a new issue now in software engineering, and many researchers have worked in this direction. However, these existing works are quite different to the Plot2API, since they accomplish the API recommendation tasks based on the source code or textual descriptions. To the best of our knowledge, the Plot2API issue remains unstudied. Although the Plot2API issue can be deemed as a common multi-label image classification, it is very challenging due to the extremely varied appearances of the plots drawn by the same API and the unnoticed visualization functions of some subsidiary APIs, as shown in these figures. Hence, we leverage a recently advanced CNN model named Efficient Net as a backbone network to develop a novel deep multitask learning approach and a novel end-to-end trainable deep learning approach named the Semantic Parsing Guided Neural Network for filling the aforementioned missing technology. SPGNN introduces an extra semantic parsing module to the Efficient Net. Then, I would like to introduce the model we have proposed in this paper, named the Semantic Parsing Guided Neural Network. The framework of SPGNN can be divided into 2 flows. As we can see, the feature learning and API recommendation modules compose the flow path of the plot-based API recommendation, while the feature learning, semantic translation, and the semantic matching modules compose the flow path of plot-based semantic parsing. Now, I will elaborate on our proposed method. The first part of our method is feature learning. Here, we choose a very recent CNN module named EfficientNet B3 as a feature learning network. We use a feature extraction network as a mapping function of our feature learning module, which can be denoted as a function. The visual feature I is a pooling result of the last convolutional layer's output. E and phi are the feature learning and its learnable parameters. Then, the semantic parsing module utilizes a semantic translation network, which consists of one fully connected layer, to to translate the visual feature learned by CNNs into the semantic representation of APIs. As shown in this figure, the visual features of a plot learned from efficient night into the semantic representations of APIs. Here, we employ the Wikipedia dataset retrained word-to-vector to attain the ground truth as semantic representation of each API. By applying the idea of learning to compare, we establish a relation network for judging if the translated semantics are identical to the ground truth. Then, the above-mentioned target can be reached by measuring the distribution difference between the normalized semantic relation scores and the labels based on the cross-entropy. A one-layer fully connected neural network is leveraged to map the extracted feature into a binary label vector. P is a mapping of the neural network with parameters omega. In the API recommendation task, we expect to keep the predicted labels be consistent with the ground truth. Therefore, we adopt the cross-entropy function for measuring such label consistency. We formulate the model of SPGNN which tackles both the plot-based API recommendation and the plot-based semantic parsing tasks via integrating their losses. Alpha is a manually tunable positive hyperparameter for reconciling the losses. After adjusting alpha, we can obtain the trained model. Now we move to the experimental setup. In this part, we will focus on the following three aspects about data size, measures, and baselines individually. We release three Plot2API datasets which are collected from Stack Overflow for evaluating our work. We present a novel Python-based Plot2API dataset named Python Plot13 dataset. It consists of 6,350 Python-related plot instances in total, and involves 13 APIs. Here is the data distribution of the Python Plot13 dataset. As we can see, the samples of different APIs suffered from extremely imbalanced. We also propose a new R-based Plot2API dataset named rplot32 dataset. It contains 114 images and involves 32 graphic APIs. This is the data distribution of the rplot32 dataset. This dataset also suffers from the extreme imbalance of data. Moreover, it is larger and possesses more categories, which makes it more challenging than the Python Plot13 dataset. As we can see in this table, some API functions are used by few images. In addition, there are some APIs belonging to the same superclass. Hence, we removed these classes from the rplot32 dataset and construct a reduced version of rplot32 named rplot14. As a supplement dataset, rplot14 removed 502 samples from the rplot32 dataset. We employ average precision AP as a performance metric for evaluating the recommendation performance for each API. The mean average precision MAP, known as the mean of APs over all classes, is adopted as a comprehensive metric for evaluating the API recommendation performance of different methods. The MAP is also known as the commonest metric for multi-label image classification. VG16, ResNet 50, Inception V1, and the EfficientNet B3 are deemed as representative deep learning approaches for image classification and are regarded as baseline methods. And last, We answer the following questions. How effective is SPGNN for API recommendation? How well do our SPGNN model perform after combining the semantic parsing module and the random erasing-based data augmentation? How well do our SPGNN model perform when training and testing across different programming languages? We compare SPGNN with 4 well-known image classification approaches. This table tabulates the MAP of different methods on different datasets. Here, we know that SPGNN outperforms the state-of-the-art baselines. The results reflect that our model is effective and can be used to assist developers in plotting. SPGNN and SPGNN plus data augmentation respectively achieved 71.76% and 75.95% MAP, and performed the best in comparison with all baselines. The Plot2API dataset is a more challenging dataset with more samples and more APIs. Our method still performs the best. The gains of SPGNN over VGG16, ResNet 50 in Inception V1 and the InfectionNet B3 in MAP are 7.24%, 15.99%, 19.57%, and 1.02% respectively. And such numbers of SPGNN plus data augmentation are 9.37%, 18.12%, 21.7%, and 3.15%. The results on our Plot14 are shown in this table. We found in surprise that all methods' performance is significantly boosted on the Plot14 dataset. The semantic parsing and data augmentation modules are 2 important parts of our model. After composing these 2 tricks, the performance confirms the effectiveness of these modules for the API recommendation. In order to evaluate the effectiveness of our method in dealing with the cross-language API recommendation, 10 developers independently pick up the shared APIs in Python Plot13, Plot32, and Plot14, namely bar, boxplot, and the plot, which is called line in our programming language. In these experiments, we employ the data of one programming language for training our model, while the data of the other programming language is used for testing. Taking the first row of results as an example, we train our model on Python Plot13 dataset and test the model using the figures plotted by our programming language. The observations on this table show that our method still obtains a similarly good results. No matter what language is used for plotting, it can recommend the APIs of Python and R programming languages successfully, as long as similar features shared among the graphics. That's all. Thank you.